Hello everyone, I'm Satyajit Pattnaik and welcome back to my channel. You're watching the Dimensionality Reduction series and today's video is on implementing PCA and LDA on a classification problem use case. If you're new to the channel, please subscribe and hit the bell icon to get notified on my future videos. Let's get started. So in our previous videos, we talked about PCA and LDA. We also tried to understand the basic mathematics behind both the techniques. We also went through the differences between PCA and LDA, how they differ in nature, how they differ in the implementation part. So if you haven't been through those videos on PCA and LDA, the link would be in the description below, or else you can go back to the playlist and check those videos and then come back. And today's video is more on the hands-on part. As I told in the previous videos, understanding maths behind the algorithms is going to be a little bit tough, but coming on to the practicals part, it's going to be super easy to understand. Because it's just a change of 2 to 3 lines when it comes to implementation part. Okay, so before implementing LDA and PCA, let's try to understand what exactly is today's use case. Now, today's use case is breast cancer prediction. That means we have to predict whether a patient is having breast cancer or not. Okay, as the name says, it's a classification problem unless we have a labeling done for each patient. Now, if we know that, let's say I have 1,000 patients and I have 1,000 patients medical information like what is the blood count, what is the RB, like what is the red blood cells. So various medical terminologies. So let's not talk about that part. From the data science point of view, let's consider that I have the traits or the characteristics of each patient's data, or you can call it as the X variables. And let's say for each patient, I know that whether whether she is having breast cancer or not. Now, if the labeling is done, that makes the problem a supervised learning problem and it's a classification problem, right? So let's go ahead and check the data because we do have two categories of breast cancer, right? It's malignant or benign. Now, malignant tumor is mostly known for the cancerous tumor mostly because breast cancer refers to cancer from a malignant tumor. Benign is otherwise termed as non-cancerous. Okay, so let's try to check the data set first and then we will try to implement that particular, like using that particular data set, we will try to implement a basic classification algorithm. On top of that, we will see what is the accuracy we are getting and all those things. On top of that, we will also implement PCA. We'll see the accuracy and then we will implement the LDA and see. Okay, so let's get started. I have already imported the libraries. So you can see the screen. I have imported NumPy library, Matplotlib, Pandas, Seaborn, and sklearn library, right? And this is how the data set is. Okay, let me just rerun this. Let me just restart and run all. So you can look at this particular thing. I have already read the data set using this particular location. And from here, I have called my read underscore CSV. So that basically makes it a data frame. So let me just quickly check the data set, how it looks like. We have restarted the kernel, so it's taking a little bit of time. So yeah, the data set looks like this. I have ID, I have diagnosis. So diagnosis is basically my Y variable. So it's either M or B. M means cancerous and B means non-cancerous, right? Apart from that, you can see these are all the characteristics, or you can say like the medical terminologies. I'm not pretty sure what each one of them means, but yeah, for us, each one of them is an X variable. Each one of them is an independent variable. We have to identify which independent variables are actually driving and helping us to understand that whether the patient is having cancer or not. Okay. And once we prepare our model, that model should be able to predict on unseen data, right? That's the main idea. So I have radius mean, texture mean, and all those things. And I do have like 32 X variables. So starting from here, it's still fractal, dimension worst. Okay, so these are some of the data set, these are some of the x variables which is present in the data set. Let's quickly go ahead and implement a small classification algorithm. So I'll not perform much steps, like not much in the feature engineering side or into the hyperparameter optimization. We are just concerned about the basic model, and on top of the basic model we will implement the basic PCA and LDA code. Okay, now once we understand the basic part, then only we can go ahead and do the advanced topics as well. So advanced topics definitely I shall be covering in one of our future videos, but for today's video it will be the basics, right? So what I'll do is I'll just convert the y variable, which is my diagnosis variable. What I'm doing is I'm just converting it to ones and zeros. So I'm using a dictionary. So I'm mapping M as 1 and B as 0. Once done, let me just show you. Now, if you don't know about value counts normally tells you what is the value count of each category. Okay, instead of M and B, if there are three categories like M, B, and X, so it will tell you for M, this is the value. So this is the total count of records. For B, this is the total count of records. For X, this is the total count of records. Okay, in this particular statement, we converted M to 1 and B to 0. Okay, so that's the reason it is showing in zeros and ones. So non-cancerous records are 357 and cancerous records are 212. So it's almost, I would say, like 40 is to 60% of ratio data, right? I'm not pretty exactly, I'm not pretty sure what exactly the percentage is, but yeah, doesn't matter. Now what I'll do is I'll just quickly read the data set. I'll define my X variable. So let me just randomly take some variables in X. 10, 11, 12, 13, 14, 15. Let it be. Okay, let's take till 20. Okay, it's running fine. Y is equal to data set dot ilog. Sorry, let's make, we don't have to use ilog for this also. Let's just directly use diagnosis dot values. Okay, so I have quickly run this. If you want to see, you can just simply type in and see what exactly X is. X is nothing but from the 0th index, from the second index, it is taking till the 19th index, till the 19th column, right? Because we are ignoring ID and diagnosis, because diagnosis is my Y variable and ID is a randomly generated ID, which doesn't make any sense. So adding this parameter in X variables will not add values to your problem statement, right? So you can see Y also. Y is nothing but an array list of diagnosis values. Let me just close it down. Now once my X and Y variables are selected, then I will just perform a small feature selection, feature scaling step. I'm just mentioning it as feature scaling. I'll use sklearn.preprocessing. I'm not pretty sure if I have, okay, I haven't imported it, so I'm importing it directly. Let's use a standard scaler. You can use standard scaler or min-max scaler, up to you. Now feature scaling, what exactly feature scaling is? We are scaling down each and every parameter to a different scale. Okay, now just a quick example. Why do we use feature scaling? Why do we use scaling? Now for example, I have a column called as height, and let's say it is in meters. So one value will be 1.75, one will be 1.7, 1.73, one will be 1.7, one will be 1.6, something like that. Now if we feed these values to computers, it will just treat them as 1.75, 1.7, 1.6, 1.5, something like that, right? So computers will just understand the numbers. Now it can also be done in centimeters, right? So when you are feeding different types of data, it is quite possible that computer prioritizes these values over this value. But when we scale it down, let's say I'm scaling 1.75, 1.73. Let's say we have two values and I'm scaling it down. Let's say What I'll do is I'll just divide it with the maximum value. So 1.75 divided by 1.75 is nothing but 1. The second value, 1.73 divided by 1.75, not pretty sure, let's say 0.98. Same goes with the centimeter values as well. Okay, so ultimately 175 by 175 equals to 1, and for this 173 by 175 equals to same, it will be 0.98. So you can see, however, the original values were in different scale. It was in like 10 decimal points, it's in 100 decimal points, but ultimately when we are scaling, both the values are same, right? So that's the basic funda of feature scaling. Okay, so I have randomly used a standard scaler. Let me just call the standard scaler. So, and then I'm transforming my data. Okay, so my X has been transformed. If you want to see X, how it looks like, this is how it looks like. It has been scaled down. Okay, my next step will be, I'm calling the model selection part, and I will be splitting my data into training and test data. So I will just write it down as train, test, split, X train, X test, Y train, Y test equals to train, test, split. I hope okay, I haven't imported that value, so I'll have to import sklearn dot model underscore selection, and we'll have to import this train underscore test split. Okay, and I'm splitting my X and Y value. Let's provide the test size as 0.2 or 0.25. It all depends upon you, and random state equals to 0. Okay. Now once that is done, again, you can just check how your X train looks like, how your X test looks like. You can do your R&D from your side. Let me just quickly run through the code. Training the, let's say we can create, let's say logistic regression model. Training the logistic regression model. So again, I will be importing my sklearn dot, I think it's under linear model. Logistic regression. I'll define my classifier as classifier, and I'll call the logistic regression function. And here you can just like randomly, I'm just passing the random state as 0, and then classifier dot fit. And while fitting, I'll have to pass my train data, right? So I'm just passing my X train and Y train. Okay, so it has been done. My logistic regression is ready. Now comes your prediction part. So what I'll do is I'm defining my Y prediction as Y underscore pred. So I have defined my classifier, right? My classifier name is classifier. So I'll call classifier dot predict, and I shall be predicting on the X data, right? Sorry, the test data, right? So X underscore test. Now I have my Y pred and I have my Y test. So I can analyze both of them and find the accuracy. So let's try to create a confusion matrix very quickly from sklearn dot matrix. I think it's okay. I think it should work. Yeah. So it's correct. So CM equals to confusion matrix. I'll pass my test data. I'll pass my prediction data. And once that is done, I will just print CM. Okay, let's print it. Okay, looks good. So the accuracy should be 63 plus 44 is 107 divided by 117. 107 by 714. Okay, so the accuracy is 93.85%. Let me just draw your draw this confusion matrix as well, and not equals to true. Okay, let's beautify our task, right? Looking good. So prediction 0, actual 0, 63, prediction 1, actual 1, 44. So it's I mean, it's not a bad classifier which has been created just few steps. Obviously it can be enhanced. And talking about real data sets in your real problem statements in your industries, you will not get data sets like this. So the data sets will be completely messy. You will have to perform a lot of pre-processing steps, a lot of feature engineering steps, then only you will be able to achieve a good amount of accuracy. Okay, now on top of that, let's also print the accuracy. Okay, so that, okay, let's give some spaces. Okay, so the accuracy is 93%. So this is the basic classifier which we have created. Definitely I'll pass on this code to you as part of a GitHub repo. The link will definitely be in the description below. So let's do one thing. Let's just copy this particular code in the PCA part, and let's just copy one by one. Let's not do this way as well. Let's directly copy it. So I'll just copy this, duplicate. Once that is done, I will just rename it to breast cancer PCA. Okay, so the same problem statement, what I'm doing is I'll just implement PCA internally. Okay, so let me run this code till a certain point of time, till the feature scaling part at least. Done, 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 done. Okay, so once, okay, we'll also have to do the train and test split. So after this, what we will do is we will implement the PCA. I'll explain you line by line. Let me just write it down first. PCA equals to PCA. Let it be open braces. I will explain you what all can be passed in the value. PCA dot fit transform. And x text equal to PCA dot transform. I think that's it. What else? We can also see the explained variance also. Explained variance equals to PCA dot explained variance ratio underscore. I think so. Not pretty sure. So here, so what I've done is till now everything fine. We have read the data set. We have done the feature scaling. We have done the train and test split. Now, the only reason why do we use PCA or LDA? So obviously this problem statement has 32 X variables, which is okay. In real scenarios, there can be 150, 200 variables. In those scenarios, there will definitely be a need of PCA or LDA. Okay, because we need to convert it into PC components and then analyze which components are giving us the best variance and all those things. So that is the main idea, right? That's why we are implementing PCA, because we are cutting down, we are doing a dimensionality reduction, right? So let's try to implement using just one component. So you can pass one n components as one. So this is one of the ways to implement it. One another way will be just passing the ratio. Like I'm just concerned about 90% explained variance. I'm not concerned about how many components are you going to select. Now obviously when you're working on a use case where there are 150 X variables, that means I'm going to create 150 PC components, right? Out of 150, do we have to use 150? No. We can also achieve our task in 50 or 30 or 20. It depends. You have to do a hit and trial. That's where you understand. So for the time being, let me just comment it out. Just create one component and see how the model behaves. Okay, done. So I'm just doing an explained variance right now. Now what is explained variance? Okay, so let me just print it out and then I will explain what exactly explained variance is. Okay, so here you can see the explained variance is 99.36%. That means now our main motive, if I pass n components as 2, there will be 2 values in the array. Okay, now what does our explained variance means? Ultimately it means that we are going to find some principal components which is the most unique in nature. Okay, so we are searching for the maximum variance so that one of the component or some of the components is unique in nature. It is one of the most unique, it is having the unique characteristics which can help us in the classification model building part. Okay, so let's go ahead, let's create our model. So same thing. Now if you want me to explain this part, I will just quickly explain. Here I am calling n components as 1. I am doing a fit transform on my xtrain because the concept is same. We are fitting and transforming the training data because ultimately we have to transform, which is okay, but we have to fit the data in the model. Test data does not needs fitting, it only needs transformation, because once the model is fitted on the training data, then only we test the model using the test data, right? So test data is never fitted. Training data it has to be fitted and transformed. So that's the reason we use fit underscore transform. Test data, we only use transform. Okay. So let me just quickly run this. Regression is ready. Prediction is ready. I'm not pretty sure if it has run properly or not. Let me just run this again. It's nothing. In the exact piece of code, I have just added this 4 to 5 line. That's it. Okay. As you can see, our model is ready. 6339. What is the accuracy? Accuracy has decreased. Okay. By using PCA, because it's just one component, right? So accuracy will decrease. If you increase your number of components, your accuracy might increase. Okay. So let's try to implement the same piece of code using LDA and see how the accuracy behaves. I'll just quickly copy paste this code. I'll make it duplicate. Once that is done, I'll just open it. From PC, I'm just changing it to LDA. Okay. Let me run the code. In the part where we have mentioned PCA, there only we'll have to do some changes, and the changes are very minimal. It's just 2 to 3 words. That's it. Let me run this till. Okay, here everything is fine. Here, instead of PCA, I'll just change it to LDA. So instead of decomposition, LDA is part of your discriminant analysis. And the method name is linear discriminant analysis. Now, if you ask me why it was PCA and why this is not LDA, why it is linear discriminant, I'm not sure. LDA equals to this. We will keep the n components as 1 because we are comparing PCA with LDA. Okay, I'll just comment this out, and maybe once you have time to run this code, you can just run this code this way as well. Okay, xten equals to LDA. Instead of PCA, I'm just changing it to LDA. Now, will this piece of code work? The answer is no, because if you remember, I told you when we were discussing about the difference between PCA and LDA, right? In PCA, we are only concerned about the X variables. In LDA, we also consider the Y variables as well. Okay, so here, instead of xtrain, if you want, I can just run this code and see how it works. It will throw me an exception because fit missing one required positional argument. Why? Because I'm not passing the Y variable, right? So it's failing. So another change will be adding your Y variable in your LDA. Once that is done, everything remains same. Okay, let me run this code. Code is successful. If I just, okay, instead of PC, I'll just make it LDA. So you can see the explained variance is 1. That means, I mean, it's performing better than PC. Okay. Because your variance is 100%. That means we have found out the most unique uh, parameter, you can say, the LDA component, right? I will call the logistic function. I'll call the prediction. I'll call my matrix. Okay, that you can definitely see, right? In the previous case, it was 63 and 39. So total number of correct predictions were 102. Here, the total number of correct predictions are 110. If you look at the accuracy is 96%. So PCA is giving me 89% accuracy and LDA is giving me 96% of accuracy. So you can take this particular example as a challenge, or you can say as a homework. Try to compare the models, try to increase the number of components to 2, to 3, to 4. Check your models slowly and steadily. You will have a better understanding which one of them is performing well. In, I would say, not all the cases we use PCA and LDA. Where we have limited variables, there is no need of PCA and LDA. You can simply use your random forest classifier or some decision tree based models, where we will be able to understand the best parameters, or you can say the best X variables. But yeah, when it comes to large data sets like with more number of X variables, I mean, it's advisable to do PCA and LDA. Okay. So that's it. Apart from that, yeah, I do have an important slide to cover as well. So this is one of the important slides I was talking about. PCA versus LDA, what to choose. Okay, I gave you a brief idea, but let us do a reading on this part. So in case of uniformly distributed data, LDA almost always performs better than PCA. However, if the data is highly skewed, irregularly distributed, then it is advised to use PCA, since LDA can be biased towards the majority class. Right? Finally, it is beneficial that PC can be applied to labeled as well as unlabeled data, since it doesn't rely on the output labels. So it doesn't really care about the Y variables, right? But on the other hand, LDA takes into consideration your Y variable. So as I told, it requires output classes for finding linear discriminants and hence requires label data. Okay. So I hope you got a basic idea about, like we already had discussed about PC and LDA theoretically. I think after this video you might have a good amount of idea on how to implement PC and LDA in the real life use cases, and what intuition can you create from the data, whether you have to choose LDA or whether you have to choose PCA, right? That's it for today's video. Next video we shall be talking about the non-linear transformation techniques, which is Kernel-PCA and QDA. Okay, so that's it for today's video, guys. Please like and share the video, subscribe the channel, and please pass the video to your colleagues. And that's it. Keep supporting. Thank you.